In the last video of this lecture, we're going to talk about the next big technique to show that there's no simple group of given order. And that is, we're going to work with subgroups of our group of small index. So I'm going to start with some review. So let's think back to when we talked about group actions, and in particular to the discussion around Theorem 3 of section 4.2 of Dummett and Foote. Let's say that G is a group and H is a subgroup of G with index n. G acts on the set of left cosets of H in G by left multiplication. What does this action look like? G acting on the coset AH is the coset GAH. So it's the left coset of H containing the element G times A. This group action gives a homomorphism from G to the permutations of this set of left cosets of H in G. But there's n of these because this group has index n. So S G mod H is isomorphic to Sn. So we get this homomorphism where you take an element G to the permutation of these cosets that you get from G. All right, well, we want to understand simple groups, the ones that have no proper non-trivial normal subgroups. But now this kind of looks like a problem potentially because we have a homomorphism from G to somewhere. And the kernel of a homomorphism is a normal subgroup of G. So what is the kernel of this homomorphism? Well, this is something that we worked out around the discussion of group actions, but just for review, G is in the kernel of phi if and only if G acting on AH is the same thing as AH for all of these cosets AH. But what is G acting on AH? It's the left coset of H containing G times A. But if this is true for some coset AH, it's also going to be true when you change the coset representative. So this is the same thing as saying the left coset of H containing GA is the left coset of H containing A for all A and G. And now this is the same thing as saying A inverse GA is in H for all A and G. And this is the same thing as saying that G is in the intersection as we go over all elements A and G of A, H, A inverse. So this description of the kernel leads to the description that kernel of phi is the largest normal subgroup of G contained in H. Okay, so if G has order n and G has a subgroup of index k, we get a homomorphism from G to Sk. And the kernel of this homomorphism is a normal subgroup of G. And we know by the first isomorphism theorem that G modulo this kernel is isomorphic to a subgroup of Sk. So in particular, the order of G modulo this kernel, which is the order of G divided by the order of the kernel, divides k factorial. So why is this helpful? Well, if we want G to be a simple group, then it can't have any proper non-trivial normal subgroups. So it would be okay if this kernel was all of G, right? Because then we would just have 1 divides k factorial. That's fine. But the kernel of this homomorphism is contained in K, which is this subgroup. Sorry, it contained in H, which is the subgroup of index K. So the kernel can't be all of G in this case. So the other thing that would still be okay here is if the kernel was trivial, if this map was injective. So that then we wouldn't be getting a proper non-trivial normal subgroup. So we would be getting, in that case, the kernel of phi is trivial. So we would need to have the order of G divides k factorial. Okay, so I'm going to pause and erase, and I will summarize the discussion that we have just had in a really useful way to show that there are no simple groups of given order. Where are we? So here's our setup. Suppose G has order n, and H is a subgroup of G with index k. Let's say that k is bigger than 1, so that it's actually a proper subgroup. So we get a homomorphism from G to the permutation group on the left cosets of H and G, which is isomorphic to SK, because there are K of these things. And the kernel of this homomorphism is a normal subgroup of G. And we know also that the kernel of this homomorphism is contained in H. So the kernel is not all of G. So that means that if G is simple, well, the kernel is a normal subgroup. It's not all of G. So if it's not the trivial subgroup, then it's a proper non-trivial normal subgroup of G. So if G is simple, the kernel is trivial. This implies that the order of G mod the kernel, which is the order of G, which is n, has to divide k factorial, because G mod the kernel is isomorphic to a subgroup of Sk. So in this case, n divides k factorial. So what does this mean? If G is a simple group of order n, and n does not divide k factorial, then this is not possible. So what that means is G cannot have a proper subgroup H of index k. And if you don't divide k factorial, you don't divide k minus 1 factorial either. So one sort of more compact way to say this is if G is a simple group of order n and n doesn't divide k factorial, then G cannot have a proper subgroup of index at most k. Okay, so let's pause and erase and then apply this idea to show that there are no simple groups of order n for some values of n. Let's take the material we just developed and apply it to some examples. First, we'll show that there's no simple group of order n where n is 3,393. That's 9 times 13 times 29. So we're going to suppose that G is a simple group of that order. This number has a prime factor of 29. So this number doesn't divide 28 factorial. So G cannot have any proper subgroups of index at most 28. Let's apply Sylow III. It says that n3 is congruent to 1 mod 3, and n3 divides 13 times 29. So you can check that that means that n3 is either equal to 1, in which case there's a normal Sylow III subgroup, and G is not simple, or n3 is 13. So if G is simple, n3 definitely has to be not 1. So what happens if it's 13? Then n3 is equal to the index of the normalizer of any particular Sylow III subgroup in G inside of G. So it's the index of the normalizer of P inside of G, which is 13. But now this normalizer, whatever it is a subgroup of G of index 13. 13 is less than 28. So this shows, with the argument that we saw earlier, that G is not simple. Let's do another example. So let's show that there's no simple group of order 6,545. This is 5 times 7 times 11 times 17. And this has a prime factor of 17, so n doesn't divide 16 factorial. So G can't have any proper subgroups of index at most 16. Let's apply Sylow III again and see what it says about n5. Well, it says that it's 1 mod 5, and it divides 7 times 11 times 17. And it's kind of easy to check that in this product of three things, the only divisors of this product that are 1 mod 5 are 1 and 11. Okay, if n5 is 1, there's a normal Sylow 5 subgroup, and your group is not simple. So if your group is simple, then n5, it can't be 1. So what happens if it's 11? And now we just do this argument again. If n5 is 11, then pick any particular Sylow 5 subgroup. n5, that is 11, is the index of the normalizer of that Sylow 5 subgroup in the whole group. So whatever that normalizer is, it's a subgroup of index 11, which is less than 16. So we see by this previous argument that G is not simple. Okay, so that's how this technique works. I think in general, it's the second easiest technique to apply to show that there's no simple group of given order. So I'll pause and erase, and then I'll say just a little bit about what else is out there. In this lecture, we've seen two main techniques for showing that there are no simple groups of order n. We've seen the idea of using Sylow III to say what we can about the number of Sylow p subgroups for each prime p dividing n, and then using what that tells us to count elements of prime order inside of our group G, and showing that in some cases that forces there to be a normal Sylow p subgroup for some prime p dividing the order. So the second main thing that we saw was this idea that if G is a group of order n that is simple, then it can't have a subgroup, a proper subgroup of index k if k is too small, where too small is going to depend on n in some way. So those aren't the only techniques that are out there. I want to at least mention that in section 6.2 of Dumb and Foot, there are a couple of extra techniques that come up. This one of permutation representations, which is really just like a souped up version of this no subgroups of small index idea that we've been talking about. The next two are more complicated. The first one is described as playing p subgroups off against each other for different primes p. And then the last one is studying normalizers of intersections of Sylow p subgroups. So I don't want to go through all of these because they get pretty intricate. And I don't want to give you the idea that classifying values of n for which there is no simple group of order n is the most important thing in group theory. It's definitely not. It's just that this is a topic that uses the Sylow theorems in a nice way, so it tends to come up very frequently on graduate algebra qualifying type exams. So in this class, if you were given a problem that was like, here's some number n, show that there is no simple group of order n, you should be able to do it either using the first technique, this one of Sylow III plus counting elements, or the second technique that G has no proper subgroup of small index. So you won't need to go through these extra ones. Okay, so aside from these like no simple group of order 56 type statements, what else can you prove with these ideas? And I just want to give you two examples. So one is something from earlier in Dumb and Foot that we skipped over at first, which is proposition 23 on page 143, which says every simple group of order 60 is isomorphic to A5. So obviously you can't show that there are no simple groups of order 60. There is one, but there is exactly one up to isomorphism. So a more complicated example of a similar statement is theorem 15 on page 212, which says that every simple group of order 168 is isomorphic to GL3 Z mod 2Z. So this every simple group of order 60 is isomorphic to A5 statement, we basically have the tools to do this now. This does involve a little bit more about this permutation representation idea, but this is something that you could understand if you read the proof without much additional effort. This statement about simple groups of order 168 really is significantly more complicated. You can certainly follow all of the steps that go into the proof, but it's pretty extensive. So I encourage you to take a look at it. And this is not the kind of thing that you would be required to understand in this course, but it's a good argument to read over to get a feeling for like how these types of arguments look when things become more complicated.